Let's talk about how gradient descent with momentum actually works. Here you're looking at the contours of a loss function, with the point at the center being the minimum we want to reach. Below that is the update rule for plane gradient descent. In this formula, theta represents the model's parameters. This could be a single weight or an entire vector or matrix. Regardless of shape, the rule is simple. We subtract the learning rate multiplied by the gradient of the loss from the current weight. The issue with plane gradient descent is that it can be unstable and inefficient. The updates tend to create a zigzag path, and if the learning rate is even slightly high, the algorithm may overshoot the minimum and diverge. If you are not familiar with basic gradient descent, I have explained it in detail in an earlier video. The link is in the description. Before we continue, one important note. Momentum relies completely on something called an exponentially weighted moving average, or EWMA. So, if you don't already know how EWMA works, I highly recommend watching the short 6-minute video I made on it. The link is also in the description. Understanding EWMA makes this algorithm almost instantly intuitive. Now, momentum fixes this instability of plane gradient descent by smoothing the update direction. Instead of using the raw gradient at each step, we use an exponentially weighted moving average of all past gradients. This quantity Vt is computed using a hyperparameter beta, usually around 0.9. Beta controls how much of the previous average we keep. Keeping it high means the algorithm considers more past values in the average, while keeping it lower focuses more on just the most recent gradients. And 1 minus beta scales the current gradient. Next task is to substitute this Vt in place of raw gradient in that original update equation. The optimization becomes much more stable. It builds momentum in consistent directions and suppresses those sharp zigzags. The intuition is simple. Momentum gives the algorithm a weighted memory of all past gradients, with recent one mattering more. Instead of reacting instantly to every tiny twist in the slope, it blends several gradients together. So if the landscape has steep vertical walls but a gentle slope horizontally, you don't get those crazy jumps anymore. All those sharp vertical components just get averaged out. This also reduces sensitivity to higher learning rates because those abrupt vertical jumps get averaged out quickly. A helpful physics analogy is to imagine a ball rolling on a landscape representing the loss function. In plane gradient descent, the ball has no mass. It instantly snaps to the direction of the slope at that exact moment, which is why the path looks jerky and erratic. But with momentum, the ball behaves as if it has real mass. And here's the key idea. The accumulated gradient acts exactly like acceleration. If the slope keeps pointing in the same direction, the ball speeds up. If the slope suddenly flips a little, the ball does not instantly reverse. It resists. This creates a smoother trajectory and helps it move faster along long, shallow valleys while ignoring sudden changes in steep directions. You may still see left-right oscillations near the minimum, but they shrink over time because beta works like a friction factor. It keeps part of the previous velocity but gradually damps the oscillations as the ball settles into the minimum. Now, one question that often comes up is, why don't we use bias correction while computing this moving average? In momentum, we don't need that. The algorithm only cares about getting a smooth direction, not an exact magnitude. Even if the early averages are biased towards zero, it does not harm learning. The learning rate scaling handles the magnitude anyway. That's why deep learning frameworks like TensorFlow, PyTorch, or Keras omit bias correction in their momentum implementation. So that's all for this video.